In this video, I want to talk about the single index model. But first, let's go back to Markowitz when he first came up with this procedure for finding the optimal risky portfolio. He said you need to have the expected returns, and you need to have the expected covariance metrics, and of course, the risk-free rate. All right, so if I use historical data, and that's what a lot of people did at first, use historical data, and you don't really have the expected returns, you have what the returns were, not what you think they will be. If you have this covariance matrix generated from historical data, you have what the covariance matrix was, not what you think it will be. So what I've done here is I've taken not 3 stocks, but 3 ETFs. I have the energy sector ETF, financial sector, and technology sector ETFs. All right, so these were their returns over some number of years, and this was the covariance matrix. So think what I need to do here. I need to have 3 estimates for returns. So if I have N stocks, I need to have N estimates of expected returns. If I have 3 stocks, I need to have this number of estimates of correlation, so that in general it's going to be N times N minus 1 divided by 2 estimates of correlations, and with those correlations I can then build the covariance matrix. So if I have 100 stocks, I will need to have 100 expected returns. I'll need to have 4,950 estimates of correlation. So I'll need to have a total of 5,050 parameter estimates. If you think about you're the actual manager of some investment management company, you have your analysts, they're in the energy sector. Okay, those guys can go through their stocks in the energy sector. They can come up with expected returns like this, and they can come up with the variance of each individual stock, and they can even come up with the correlation perhaps of the stocks within the energy sector. Then you have a financial sector analyst, and this person can come up with the expected return for all the stocks in that sector. They can come up with the estimates of risk and the correlations of the stocks within that sector. But the real problem is, how can I figure out the correlation of stocks in the energy sector with stocks in the financial sector with stocks in the tech sector? And there's no one analyst that can really do that. So that's a problem. So what do we have to do? We use historical data, and that tells me what those relationships were. I can do that estimate relatively quickly, but the problem is it gives me bad results. And that's where people had trouble with the model, and they didn't actually use it. They said, yeah, this is brilliant mathematically, but it doesn't work because I have bad inputs, I have bad outputs. So in this example, and this is not unusual, the result is you put 108% of your money into one asset, into the energy sector, and you short the technology sector by 15%. Now, can a prudent person who's subject to being sued say this makes sense? And the answer was no, this doesn't make sense. We need to have something else. We need to develop a different way to do this. So let me talk about how that different procedure would be developed. So think about the CAPM. What does the CAPM tell me? It says the expected return on stock is equal to the risk-free rate plus the beta of that stock times the expected return on the market minus the risk-free rate. So this is going to be, let me rewrite this, and I'll subtract the risk-free rate. I'm going to drop these E's for expected return. So the expected return on the stock minus the risk-free rate is equal to the beta of the stock times the market risk premium, or the excess return on the market. So let's write this in an easier way. I'll use capital R to represent excess return. So this lowercase r is the raw return minus the risk-free rate. So capital R is the returns above the risk-free rate. That's equal to, I'm going to throw in an alpha here, plus beta times the market risk premium. Alpha, if the market is efficient, alpha is equal to 0. But I can sit over here and have my analyst that's looking at the energy sector say, you know what, the alpha for the energy sector is 1%, because I think I know more than the market, and I think that the market just believes the return is going to be beta times the market risk premium. I think it's going to be 1% more than that. a guy in the tech sector can say, you know what, tech stocks I think are going to be down 1.5%, so they're going to underperform what the market thinks. So I can put that information in and I come up with what my returns will be. Now let's just go through some of the algebra of this and think about what we need. I need to have returns. So how I can get returns, so return for the energy sector would be equal to the alpha for the energy sector plus the beta for the energy sector times the market risk premium. The return for the tech sector would be the alpha for the tech sector plus the beta for the tech sector times the market risk premium. The return for the financial sector, alpha for financial plus beta for financial times the market risk premium. Okay, so the first thing we need to estimate is the market risk premium. Where does that come from? Well, I want to save that for another day and say we're going to outsource this, and we have our macroeconomic guy, and our macroeconomic guy says market risk premium is 5%. Then where do these alphas come from? The alpha comes from my energy sector analyst, my tech sector analyst, my financial sector analyst. So I got those taken care of. What about beta? Well, beta I want to save for another day too, but basically I have to find beta using some method, maybe a regression method, maybe some type of fundamental beta, but I need to find what hopefully is a forward-looking beta. At this point I can find my returns, and this is very reasonable to ask my sector analyst to do. Okay, so the next thing I need to do is think about the covariance matrix. So I also need to have the covariance matrix. So I know this. I know the risk, the total risk of an individual stock is equal to the beta of that stock times the variance of the market plus the residual variance. So this is, like I said, total risk. This is the market or systematic risk. This is a firm-specific or idiosyncratic risk. So the total risk of the stock is a market risk plus the idiosyncratic risk. Then I think the key insight, the best part about this model, the single index model, is coming up with a covariance matrix. So the covariance matrix is going to look like this. It's going to be the beta of stock I times the beta of stock J times the variance of the market plus, and it's going to have the expected relationship between those two stocks. This, of those error terms, this is going to be equal to 0. And think about the reason for this. I know that the model is not going to describe the energy sector perfectly, or the tech sector, or the financial sector. It's not going to describe any individual asset perfectly. There's going to be some error in this. But the error on an individual stock should be unrelated to the error on another stock. So the market model, the CAPM, is not going to predict the returns for Apple perfectly. Hopefully it comes close, but it's not going to do that perfectly. It's not going to predict the returns for GM perfectly. So there's going to be error left over for Apple and error left over for GM. But I'm assuming those two errors are unrelated. So the fact that underpredicted, or the market model underpredicted Apple, shouldn't tell me if it's going to under or overpredict the return for GM. So those things should be independent of each other. So what this is going to allow me to do is get a better estimate for the covariance matrix. In other words, if I look back in history and I see how, let's just take the examples of Apple and GM. I look and see how they move together. There are two bits of information in that historical data. There's the true relationship between those two firms. There's also noise. There's also random stuff that happened that disguised what that relationship looked like. So when I get my historical estimate of the covariance matrix, that's telling me the true relationship plus the noise, and I want to get rid of the noise, and basically this last term right here is the noise term. So I wind up having a better estimate of the true nature of the relationship of these stocks. Furthermore, I want to have not the past looking betas, what beta was, but I want to have some better estimate of what I think beta will be, so I can have a forward looking estimate now of what I think the correlation or the covariance between these two assets is going to be. So that's going to allow me to get a covariance matrix and have an easier time with the inputs. So let's think about what those inputs need to be. I need to have n expected returns. So each individual stock, I need to have an estimate of their expected return. I need to have, well, actually not expected return, I'm ahead of myself. Let me put it to you this way. Eventually I need to get there, but I need to have n estimates of n alphas. I need to have n betas. I need to have n estimates of the idiosyncratic or the firm specific risk. And I need to have one estimate of the market risk premium and one estimate of the variance of the market. So I need to have 3n plus 2 estimates. So if I have 100 stocks, I need to have 302 estimates. And another thing you can think about with the beauty of this, if I have my energy sector and tech sector people, they don't need to come up with a better estimate of the correlation between those two, the stocks in those two sectors. This beta, if they come up with a better estimate of the beta, what it tells me, they have a better estimate of what they believe the relationship with the market will be for energy sector stocks. They also have, my tech sector guys have a better prediction of what the relationship with the market will be for the tech sector. So let's go back to Apple and GM. I know I'm skipping around a little bit. Go back to Apple and GM. That beta for Apple is going to tell me the relationship of the market and Apple and what that relationship will be going forward. So I've done whatever analysis to get that better estimate of beta that tells me that relationship going forward. Same thing with GM. So my GM guy has told me the relationship of GM to the market going forward. Now, if I know the relationship of Apple to the market and GM to the market, I therefore figured out the relationship of Apple to GM. So that's the important thing. If I know the relationship of Apple to the market and GM to the market, I know the relationship of those two stocks to the market. And that's what the single index model allows me to do. Now, let me show you some results from some actual data real quick. Okay, so here's the results from the single index model. My inputs, the alpha and the beta, they give me my returns. And I didn't do any analysis here, I just picked the 1 and the 1.5. So this is going to give me, my analyst is going to give me these alphas, and this is going to give me a more reasonable return of what I expect to happen going forward. Many times you'll have the returns be negative because maybe that particular stock or that particular sector was negative over whatever historical time period you used. So that number would be completely bogus. This is going to give me much better results for expected returns. And the way that happens is it's the 1% plus the beta times the market risk premium. The 1.5 plus the beta times the market risk premium. Okay, so how do I come up with the covariance matrix? I want you to notice that the variances are the same. Okay, I messed that up, but the variances are all the same, right? The difference is going to be in the covariances. Those are going to be the ones that are different. So how did I come up with those numbers? Well, the covariance of energy with financial is equal to the beta for energy, the 0.6564, times the beta for financial, 0.7652, times the variance of the market, the 0.0208, and that gives me that answer. The variance of the market is going to usually be taken from historical data because we can think, well, the variance of the market as a whole doesn't change that much. Excuse me. Doesn't change that much over time. But we can also, if you want to, you could have your analyst put in a number for that. So with this more reasonable estimates, we come up with a more reasonable estimate of what the different weights for the stocks are in the optimal risky portfolio. So if I'm looking at the output the historical data gives me versus output the single index model gives me, it's easy. This one looks like it makes more sense. The single index model certainly looks like it makes more sense. So the final analysis here is this. You're going to have two different sets of inputs. Here are the inputs for a historical model. Here are the inputs for the single index model. And the procedure, the optimization procedure is the same. We haven't talked about that yet. But you have the returns, you have the covariance, you have the returns, you have the covariance matrix. It gives you the output. And the output's different only because the inputs are different. So the whole thing about the single index model is come up with a better estimate of what those inputs should be and plug it into your optimizer, which is a different subject. And for exactly how do we estimate the betas and the market risk premium, that's something left for another video.